This is Unit 7, Video 12. In this video, we will talk about an important concept dealing with delta H, enthalpy. Enthalpy, remember, is the amount of heat released or absorbed in a chemical or physical change. Now, enthalpy is an extensive property, which means it depends on how much matter you have. So the more matter you have, the higher the value. Remember that an intensive property is something like density. Density doesn't matter on how much stuff you have. The density, no matter how big the sample, the density is the same, but enthalpy is extensive. And so what we could do is we can manipulate an equation, and we'll have to manipulate the delta H accordingly. So this will be a discussion of enthalpy manipulations. And it's pretty simple. The concept goes like this. Here you have an original equation along with the delta H. Notice that this reaction is releasing 1204 kilojoules, and this would be related to the balanced equation. So if you burn 2 moles of magnesium, you'll produce 1204 kilojoules. That's the idea. If you decide to double the coefficients, double the moles from 2 to 4, and then everything has to get doubled, the oxygen goes from 1 to 2, magnesium oxide from 2 to 4, you simply double the kilojoules on the right. And if you half it, if you divide everything by half, so from 2 down to 1, and then you can divide the 1 and get a half. You could have halves for coefficients. That's not a problem. You can have any fraction number, and then this gets halved as well. Notice that the delta H also gets halved. Now, usually this is the form that you'll see the equation in, because it's usually based on 1 mole of the substance that you're burning. So usually you'll actually see it like so. So notice anything you do to the coefficients, you then do to the delta H, because delta H depends on how much stuff you have. You can also reverse the reaction. So here we have the original equation, the one that has just 1 mole of magnesium. And here it says delta H is equal in magnitude, but opposite in sign for the reverse reaction. So if you simply flip the equation, notice here I have magnesium for the reactants, magnesium oxide for the products. If I flip it to where the magnesium oxide is the reactant and magnesium is the product, then I simply change the sign from a negative to a positive. Now what this means is if you burn magnesium with oxygen, combine magnesium with oxygen, it'll produce 602 kilojoules. So if you want to split the magnesium oxide back into magnesium and oxygen, you've got to put in that same amount of heat. So in this case, the reaction is reversible, and the delta H is exactly the same. Now, the enthalpy change depends on the state of the reactants and your products. So, for example, here we have a different reaction. This is methane combusting with oxygen to give you CO2 and H2O. The delta H for the system, or for this process, is negative 890 kilojoules. Now, if you take a look, here we have a liquid water being produced versus a gaseous water being produced. And this changes the delta H. Notice it changes the delta H by about 80 or so kilojoules. And the reason for this is because going from a liquid to a gas requires you to put in about 80 kilojoules. In fact, this process here, 2 moles of water, since we have 2 moles of water here and 2 moles of water here, if you want to boil 2 moles of water from a liquid to a gas, you have to put in about 82 kilojoules of heat. This is the heat of vaporization of water. This is a physical process, but we can show it as a chemical reaction or just as a reaction. So the difference here between these two values is actually 82 kilojoules. So you have to put in 82 kilojoules, and so in this case, if you form water liquid, you release 890, but if you form water gas, you release 808, because 82 of that had to boil the water, if that makes sense. So you have to watch for your state symbols. So watch out anytime you have a reaction. If, for example, CO2 were a solid, it's possible, then that would be a different number, and so forth. Now, where this comes in is in something called Hess's law. We're going to focus essentially in this video on Hess's law. And Hess's law says we can calculate delta H, the heats of reactions, from the delta H values of other reactions. We're going to use one reaction to determine the delta H of another. What this means is that a small number of experimental measurements can calculate the delta H's of a vast number of different reactions, and this is really neat. This is because all the reactions are connected together. And so here's a little diagram. What you see, these are the reactants for the combustion of methane that we just saw. And these are the products, CO2 and H2O, liquid. And that we said costs 800 or produces 890 kilojoules of heat. Now you could have done this in a stepwise fashion. You could have, for example, reacted the CH4 and O2 to first give you carbon monoxide and water. And then you could have converted the carbon monoxide and water to the final products. And you'll notice that the total heat here will actually match. If you add these two numbers, you'll get the 890, negative 890. So all the reactions actually match. And this is actually something called a state function in chemistry. We're not going to go too deep into this, but we mentioned this. A state function allows you to go, it doesn't matter how you got there, but there are many different paths to get to the final answer with state functions. So this doesn't make too much sense. We'll actually do a few example problems, and that hopefully will make sense what we mean. So here is how we're going to use Hess's law. We'll list the reactions along with their heat values, change in heat values. Then we'll manipulate the reactions as needed so that we match a target equation that we want to come up with. We can combine the reactions then that we've listed, making sure to cancel out. We'll cancel out anything that appears on opposite sides. So if you have a reaction that has O2 on this side and O2 on this side, these O2s essentially cancel out. And then we'll combine, or we'll add up anything that appears on the same side. So if you had O2 on this side of the reaction and O2 on this side of the reaction, you'll essentially eventually have a 2O2. And you'll see how that works. And this is actually very similar, or it's exactly the same. If you've ever learned about solving systems of equations in mathematics, where you list a bunch of equations and then you add them up, and you come up with a final equation, this is actually the same thing. Math has actually paved the way in order for us to be able to do this. Alright, let's go ahead and dive in and do a few example problems, and it'll make a little more sense. So we have two reactions we're going to use along with their delta H's, and this is going to be our target equation. We're going to get the delta H of this third equation. Hess's law allows us to combine these two reactions together and produce this final equation. Now what you'll need to do is these two equations will have to match the last equation. So for example, the last equation says that you have carbon solid on the reactant side, on the left side. That carbon solid will come from the first equation. So the first equation will actually remain untouched. It sits as it needs to sit in order to get carbon solid on the left side. The second equation, however, will provide CO2 for us. Now CO2, notice, is on the right side of our equation, on the product side. So what we'll need to do is we will need to flip this equation. You can go ahead and write flip if you'd like here. So that equation will need to be flipped. Now as we flip the equation, we're essentially making products reactants and reactants products. And then remember that the sign of the delta H will also flip. So what we'll do here is I'll rewrite this equation. Let's go ahead and rewrite this equation with the products as and reactants flipped. So we have CO2 gas for our reactant now, arrow, and I've got CO gas plus half of O2 gas. Now the delta H for the reaction is now not negative, but positive 283.0 kilojoules. I'll go ahead and cancel out or cross out the equation that I've manipulated, so that way I don't have to use it. Now, if I've done this right, these two should match up to give me my final equation. I'm going to go ahead and rewrite the first equation so you can kind of see it side by side. So I'm simply rewriting the first equation down here. This is carbon solid plus O2 gas to give you CO2 gas. And the delta H is the same as up above. So I'm not doing anything to the first equation. Negative 393.5 kilojoules. So what we'll do now is show you how the two equations cancel out to give you this final equation that we're looking for. This is our target equation. Let's call this the target equation. So notice the target equation has carbon solid on the left. That's exactly what we have in these two equations. Notice that I've got CO2 on the left side and CO2 on the right side. Now the rule said that we cancel things out that appear on both sides, so those two get canceled out. Now you also have CO on the right side that doesn't get canceled out, so I'm going to circle everything that does not get canceled out. And then what you see is you actually have O2 on the left and on the right, so this will cancel out. However, you have 1 mole of O2 on the left and a half a mole of O2 on the right. So what will happen is this half will cancel out with 1/2 of this to give you 1/2 that's left over, if that makes sense. If that's a little confusing, if I had 2 moles here and 4 moles here, then the 2 moles will cancel out 2 of the moles and leave 2 behind. That's how it works. So notice what we've done is now the whole equation, things that we haven't canceled out, we got carbon solid, and then we have a half of oxygen that was left over as a gas, and then we also had CO as a gas. Notice this matches exactly this equation, the target equation that we were going for. And that's the whole point. And if we've done this correct, what you can do now to get the delta H, you can simply add these delta H's. And that's the beauty of the system. So we can add those two numbers and actually get ourselves this final delta H. Now it looks like you'll essentially do 283.0 minus 393.5. So 283 minus 393.5, and you get negative 110.5. This is negative 110.5 kilojoules. And that is now the delta H for the reaction. Notice we were able to get the delta H of an equation that we didn't have to perform the reaction for. So this is the beauty of Hess's law. You can determine the delta H of a new equation without having to perform the reaction. And when you do perform it, to confirm it, you will find out that it exactly matches. Hopefully, as long as there's no error committed in the reaction itself. Alright, let's do one that's a little tougher. Let's go ahead and do example 15. The same thing, except 3 equations to combine. So again, we're giving a target equation. Our target equation here has 2 carbon plus hydrogen give you C2H2. That's our target equation. We're going to try to find out the delta H of this equation by combining these other 3 reactions. So notice what we need is I need to have 2 carbons on the left side of the equation, 2 carbon solids. Now my carbon solid comes from the second equation, but I need 2 of them. So what I will do is I will manipulate the equation so that way it gives me 2. What I'm going to do is rewrite the equation down here, and I will multiply by 2. So go ahead and put times 2 if you like for the equation. So I'm simply going to double it, not change it, but double it. And I've got 2 carbon solid plus 2 oxygen gas, giving me 2 CO2 gas. Now my delta H also must get doubled. So my delta H will now be, if it were 400, I'd be 800 minus 12, so 788 kilojoules. Now this is negative, make sure you keep the sign still, negative. So notice I doubled it, so I get to double my equation here, my delta H. So we can cancel out this reaction. Looks like if I take a look at hydrogen, H2, that's going to be my second compound. The H2 will come from this third equation. Notice I have one H2 and I need one H2, so most likely I will keep the H2, that reaction as it is. So let me just rewrite it. I'll go ahead and rewrite it and put no change on it. Just go ahead and rewrite it, no change. That way so you can see as they line up. So I'll go ahead and put H2 gas plus a half O2 gas to give me H2O water, liquid water. And the delta H remains the same. Okay, you can go ahead and cross that one out because we have rewritten it. And then notice that the third equation, or the ones that I haven't done yet, this third substance, C2H2, is on the right side and there's only 1 mole of it. Now C2H2 comes from the left side of the equation, and there are 2 moles of it. So what I will need to do with this equation is I will need to flip it, and I will need to half it, divide by 2. So all the way down here, why don't we put flip and half. I'm going to flip it and divide it by 2. So what I've got is I've got my 4 CO2 that are the products become 2 CO2 as reactants. So I've got 2 CO2 gas. My 2 waters here, liquid, become 1 water, so H2O liquid. And then I have my C2H2 as a gas, and my 5O2. Now, I'm going to have to divide that by 2, so 5 divided by 2 is 2.5, so let's do 2.5. 2. Now my delta H then, for this equation, we'll have to take this number, which is negative, and make it positive, so this will be positive, and then we'll have to divide it by 2. So 2600 divided by 2 should be 1300, so we got 1300 kilojoules. Okay, we can go ahead and cancel this equation out. Now, if we've done everything correctly, what should happen is our final equation should come out like this. When we cancel everything out, all we should be left with is this simple equation. So let's see what we can cancel out. Now, you'll notice that there are 2 CO2 on the right side and 2 CO2 on the left side. Anything on opposite sides cancel out. Now, when we say on the right side, we mean on the right side of the arrow and the left side of the arrow, reactants and products. So CO2 cancels out. Now, if you take a look at carbon, I have 2 carbon here. This 2 carbon should remain. And notice nothing cancels it out. There's no carbon anywhere else, so that will remain. The hydrogen, likewise, right below it, we got 1 mole of hydrogen. That does not cancel out with anything. Notice that the water, H2O, cancels out. H2O liquid will cancel out. And C2H2 remains. That's what we want. And oxygen. We have a bunch of oxygen. Do the oxygens cancel out? Let's see. We have 2.5 moles of oxygen on the left of the arrow. Lo and behold, we have 2.5 moles of oxygen on the right side of the arrow. So the oxygen, all the oxygen cancels out. What we're left with is what we wanted, which is 2 carbon, solid, plus hydrogen gas, to give us C2H2 gas. Exactly what we wanted. Matches exactly this equation. So what we can simply do now is add up all the delta H's to get the final delta H, and that's exactly what we'll do. So the delta H for this final equation, go ahead and add it up on your calculator. So you've got negative, make sure you keep track of the negatives. So essentially I'll do 1300 minus 788 minus 286 for a total of 226 kilojoules for the reaction. And this is my final answer. And that's how Hess's law is done. So we'll give you quite a bit of these types of problems to practice. They are very fun. It's like solving a puzzle. So we'll see you in the next video.